First bit of important information is that the first quiz in this class is going to be on Friday. Um, so, you know, skim through, read through your notes. I'll just be answering short answer questions um, about what I said in class. And then we're going to get into this example problem to start. Who remembers what we're talking about in this class? Right, heat transfer. And the first one we did was conduction. So we're going to do an example problem with conduction. We're going to take this 1 meter by 1 meter window. And the thickness of the window is 2 centimeters. That's 0.02 meters. And the front side has a temperature of 15 degrees Celsius. And the back side has a temperature of 20 degrees Celsius. And we're given that the coefficient of thermal conductivity, kappa, is 1.05 watts per meter Kelvin. And we're going to assume that the temperature varies linearly with x. Remember, x is parallel to the path of the energy transfer. So you could think of x as being the distance into the thickness of that panel. And we want to calculate Q dot. And then second, we're going to think if our system is on the 20-degree side, what's the Q dot we would use in the differential form of the first law? Okay. So the formula is Q dot is equal to kappa times area times dt dx. Since that temperature varies with x, we can also think of it as kappa times the area times the difference in temperature divided by the thickness, parallel to the energy transfer. And also, this formula always is given with a negative sign, but we're not going to think about that. That's a direction thing, and we'll think about the direction separately. Okay, so what is the A? You can kind of make sense out of what A would be based on what it does to this equation. If you're imagining energy flowing down like a channel down a pipe, the thicker the pipe is, the bigger your heat transfer would be. And so if you think of this as energy flowing down a pipe, the thickness of the pipe, the width of the pipe would be the area, this area, the 1 meter by 1 meter. Okay. So our Q dot is equal to 1.05, that's the kappa, times the area 1 squared. And now times the difference in temperature divided by the distance that the energy has to travel. So this is 5 degrees Celsius divided by the distance that it has to travel is 0.02. One thing quick about the temperature. Anytime that you're doing a difference in temperatures, remember that Kelvin and Celsius mean the same thing. So like in the formula here, the units are Kelvin. So you might think you have to convert the temperature to Kelvin, but, and you could express both of these in Kelvin. This would be what, 278 Kelvin, and this would be 293 Kelvin. And then you'd subtract them, and you'd get the exact same difference in temperature as you do in Celsius. Okay, so if all you're doing is subtracting two temperatures, like in a difference like that, you can leave it in Celsius or put it in Kelvin or whatever. Okay, and so if you do this calculation, you get, I think that's 262.5 joules per second, which is 262.5 watts. So that's how much energy is transferring. And what direction is it going? Is it going out of the page or into the page?
Out of the page.
It's going out of the page because it's always going from high temperature to low. So now the question is, okay, we've figured out the magnitude and the direction of that heat transfer. Now imagine that our system, because when you use the first law, you always have to choose a system. So let's say that our system is on the back side of this. Think of it as like our system is the inside of the room. What would we use here? Well, so if our system is the 20-degree side, is energy being gained or lost to our system?
Lost.
Right. So energy is lost through heat. And so is that Q dot positive or negative when we go to the first law? All right, it is plus or minus 262.5. 50-50 chance it's minus. So remember that Q and Q dot are positive if energy is coming into your system, like it is in a heat engine, and it's negative if energy is being lost to your system.
How to know? How to know if we gaining or lost?
Well, you just have to think about the direction. So we know that heat is always going to go from the higher temperature to the lower temperature. And so so in this case, it's going to go from the 20-degree side to the 15-degree side. Okay. So if it's going from the 20 to the 15 and our system is the 20-degree side, then it's leaving our system and going to the surroundings. Any other questions? Okay, the next type of heat transfer that we'll do is radiation. Any object that's above 0 Kelvin. Okay, that's 0 Kelvin, not okay. Temperature radiates energy. And the form of this energy is electromagnetic waves. Well, it turns out that this energy is radiated in packets and not it's not as continuous as was originally thought, and that was really the impetus for people to develop quantum mechanics. But for us in classical physics, we're just assuming that there's this smooth relationship between energy, radiation, and temperature. And the most important distinction about radiation compared to the other question?
I mean, I don't know if you'll answer it, but is there a so it's any object, like if even if it's extremely cold,
Right.
is there a difference between that kind of radiation and like a light bulb glowing? Or?
No, that's what it is. Yep. A light bulb glowing, the only difference is they all emit electromagnetic radiation. A light bulb glowing just happens to be emitting visible, electromagnetic waves in our visible spectrum. Some range of electromagnetic waves is visible light. A different range of wavelengths is radio waves or gamma waves, or all these different types of radiation are just different wavelengths of the waves. And so we can't see a very cold object radiating just because it isn't visible light, but it still is radiating energy. Yeah.
So is radiation just like a side effect of like particles moving around?
Yeah, that's right. Yep. Yeah, not just particles, but charged particles. Right. So the motion of, remember for you in physics 2, the motion of charged particles creates magnetic fields. The changing of magnetic fluxes creates current. And so that one after another flip-flopping motion of created current, created electromagnetic fields, created current, created changing electromagnetic fields is what a electromagnetic wave is. It's all super cool. That's definitely not my area, but it is really cool. Okay, so any object above 0 Kelvin radiates energy through electromagnetic waves, and electromagnetic waves don't require a medium. So radiation doesn't require a medium for transfer. For energy transfer. That's good news for us because all of the energy on Earth comes from the sun, and that energy would not be able to get here if there was no way to transfer energy without a medium. By the way, okay, this is kind of wasting time. But it's cool. Do you know when people first made the connection between electromagnetic waves and light? Like, there's no obvious reason to believe that light is an electromagnetic wave. But so electromagnetic waves obey the Maxwell's equations, okay? And under certain simplified conditions, Maxwell's equations simplify into well-known differential equation called the wave equation. Okay, and based on the numbers of electromagnetic waves, like punching stuff in, people were able to calculate the wavelength from the wave equation. All this is very complicated math, but people were able to calculate the wavelength, and then from that they were able to calculate the speed that electromagnetic waves travel through space. And when they calculated that, all totally like theoretical, just doing complicated differential equations, they came up with the exact speed that people had measured for the speed of light. So there was no reason at that point to think light was an electromagnetic wave, except people are just like, that's just would be too weird if they both had the same speed. So at that point in the 1800s, people were like, light is most likely an electromagnetic wave, and that turned out to be the case.
Was there any idea what that was before? Like,
No.
Philosophic idea
Nope.
of what light was?
I'm sure people thought about it as particles and whatever. I don't know the history of it, but yeah, I've never heard of a competing thing. They're just like, it's light, and light is light, you know. Okay. So radiation follows the Stefan-Boltzmann law. This is like a fundamental law of nature, you can think of it. Fundamental law of physics. And it says that Q sub E dot, so this is the heat that's emitted by a body. So what we're talking about here is the emitted energy coming from any object above 0 Kelvin. And it's equal to the Greek letter epsilon times the Greek letter sigma. These are constants that I'll tell you in a second. Times the surface area of the object, times the Kelvin temperature to the 4th power, where epsilon is called the emissivity. And that's just a pure number from 0 to 1. 1 is perfect absorber. And 0 is a perfect reflector. So you can think of this one as like a matte black. The perfect reflector, you can think of that as like a shiny white. So you're familiar with this idea of emissivity, not from emission of energy, but from absorption of energy. Like if you're out in the hot sun wearing black clothes, you get hotter a lot faster because the dark colors, the black, is absorbing energy. And if you're in white clothes, you stay cool more because it doesn't absorb that energy into your body. It reflects it back into the atmosphere. That's for absorption, but it works the same way for emission of energy. So if you're wearing all black on a hot day, you're absorbing more energy from the sun, but you're also emitting more energy. So why does the absorption win in that case? Well, the absorption wins because the temperature of the sun is a lot hotter than the temperature of your body. Okay, so even though you're emitting more energy if you're wearing black, you're absorbing way, way more than that more than enough to make up for it. The Greek letter sigma is called the Stefan-Boltzmann constant. That's just a fundamental physical constant. And it's equal to 5.67 times 10 to the minus 8 crazy units, watts per meter squared, Kelvin to the fourth. A is the surface area of the body. Bless you. And capital T is the temperature of the body in Kelvin. This one, since the temperature does not appear as a difference, it doesn't appear as two temperatures subtracted from each other, you have to use Kelvin in this case. Kelvin and Celsius are totally different in this case. We're talking about instantaneous temperatures. Okay, well, the Stefan-Boltzmann law doesn't give net radiation. So if you think about it, this law only gives us half of what we need in order to use radiation in the first law. So this is not useful for the first law. Because the problem is we can calculate how much energy is going out of a body due to radiation, but this doesn't give us a way to calculate how much energy is coming into the body from radiation. And that's really what we need, is the change in it, the total change in energy. Well, there's just one simple case where we can use this. So there's one simple case where we can calculate the net radiation. And that is for a smaller body surrounded by a larger body. And so in that case, we can get a net emission of energy, and Q dot, this is a net, is equal to the emissivity times the Stefan-Boltzmann constant times the surface area of the smaller body on the inside times the quantity temperature of the body to the fourth minus the temperature of the surroundings to the fourth. So let me write all this. So this is the surface area of the smaller body. This is the temperature of that B is for body, but this is the smaller body. and this is the temperature of the surrounding body. Well, all you have to remember is this is giving you a net emission of energy from your smaller body. And so if this is going to be positive, the smaller body temperature has to be bigger, so you can remember based on that what the TB and TS are. But the key thing is this equation. This is the case where we can use radiation with the first law. Let's say with the differential form of the first law. Okay, any questions about that? So this one is the more fundamental law, but it won't be so useful for us in this class because we can't put it into the first law of thermodynamics. This is the simple case, special case, but this is the one that we can use with the first law. And again, just like with all these heat transfer equations, you're going to have to think about what's the body that what's your chosen body, what's the system that you're isolating. You'll have to think about the direction of this energy flow, and based on that, you'll have to choose the sign of Q dot. Okay, just like we always will with the first law. And then the last type is convection. This is where heat is carried to a new location by a moving fluid. An example of this is wind chill. Have any of you guys ever in a sport had to have an ice bath on your foot? Like you sprain your ankle, you have to put your foot in an ice bath or something. Okay, so here's an experience from having an ice bath. You put your foot in this ice water and it's so cold, it hurts like crazy. And then it starts to feel a little better and you're like, okay, my foot's getting numb, this isn't going to be so bad. And then the trainer or whoever comes in and stirs the water and it suddenly is horrible again. It's because the high temperature of your leg heats up the water nearby your foot, and so it doesn't feel as bad. And if you move that warmer ice water now farther away from your leg, suddenly it's cold again. So that's convection. Okay, convection is why ice baths are so terrible. And the formula for convection is that Q dot is equal to a constant H times an area, and I'll talk about what these are in a second, times the quantity temperature of the body minus temperature of the fluid. Temperature of the fluid. So if the temperature of the fluid is hotter, then energy is going into the body. If the temperature of the body is hotter, then energy is leaving the body to the fluid. H is, so I said that the Stefan-Boltzmann law is a fundamental law of physics. This is not a fundamental law of physics. You can think of this as kind of like a curve fit. This H is just a catch-all. Constant that is measured experimentally for the specific kind of fluid flow that you're dealing with? And it takes a lot of things, go into this H. It has to do with how well the material conducts energy and how fast the fluid is moving and all this different stuff, but it's all just built into this constant that you measure in an experiment. A is not the total surface area of the body, it's the surface area of the body that's exposed to the fluid flow. So if only the top of a body is exposed to the fluid flow, then this is just the area of the top of the thing. So the surface area of the body that's exposed to the fluid flow. And then TB is the temperature of the body. And TF is the temperature of the fluid. Okay, so yes.
So when you say surface area of the body that is exposed to the fluid flow, so let's say like we are heating like a pan
Mhm.
with the heat on
Yeah.
You mean the surface area of
Yeah, so this would be like if you're heating a pan or an object by rushing hot water across it or hot air across it. So it's not exactly like a stove, but I think
You had a pot of boiling water and then you stirred it to make it like the entire thing well
yeah,
edges, the
yeah,
middle of the pot.
yeah. So you can imagine if you have an object. I have an example here that I don't know if we'll get to today, but where it's a microchip that's embedded in a circuit board, okay, and you're trying to keep that microchip cool as it goes through operations, okay, but this thing is embedded in a board, okay, so the cooling fluid, either the air or liquid or whatever, doesn't have access to the whole chip, okay, it only has access to the part that's poking out of and so we'd only be talking about the surface area that's poking out. We wouldn't be talking about the stuff that's embedded in the silicone or whatever. Silicon, not silicone.
And why is Q dot doesn't have a subscript E?
You could put it on for any of them, but in any case, I'm just using how they normally write these. But they all
Mean the same.
Yeah, they all mean the same thing. Basically, like you do the calculation to get a magnitude, and then you think about, is energy going into my system or out of my system in order to determine the sign that you'll use in the first law. Okay, so let's do an example. So this is a convection example. So let's say that we have a gearbox. It's just this machine where you input a torque on one side and it outputs a torque on the other side, and it's done by gears on the inside of the box that just change the gear ratio. So here is the boundary of the box, and inside the box are two gears. You have to imagine these have teeth, otherwise this wouldn't work. And these have different sizes. Like all gears. And the input is an amount of work that is done to this shaft to rotate it. So this is an input amount of work, W1. And the output is gears always switch the direction of rotation. So the output is an output work, W2. And I don't know, have you ever seen calculations of work for rotating objects? So the work done by a rotating object is the moment times the angle that it goes through. So you could calculate both of those pretty easily. And the surface area, let's say the outer surface area, after like 40 minutes, my computer loses where the stylus is. Okay, so the outer surface area is 0.1 meters squared. And the box is cooled by convection. And that constant that has been measured experimentally beforehand is 0.171 kilowatts per meters squared Kelvin. Well, kilowatts means we could also write this as 0.171 times 10 to the third watts per meter squared Kelvin, if we want to keep everything in SI units. And the temperature of the box is 300 Kelvin. And the temperature of the fluid that's cooling the box, whether it's air or some other gas or some liquid, is 293 Kelvin. And we're told that the magnitude of the input work is 60 kilowatts. So first, what's the rate of heat transfer? Through convection? I'm sorry, I know I'm making you stay over, but I'll do this fast and then you'll be able to get to some problems after this. And then second, if this is in steady state, what's the rate of work output, at that second shaft? Okay, well, the heat transfer is going to be Q dot is equal to the H, so 0.171 times 10 to the third times the area times the temperature. You can just do the bigger one first. 300 minus 293. And we get 119.7 watts. So every second, there's a heat transfer of 119 joules, 119.7 joules. And now we're going to make our system the box. And so now we can think about some directions. So is the box gaining or losing energy through heat? Yeah, so the box is losing energy through heat. And so is Q dot positive or negative? I didn't hear what you said, but I'll give you the benefit of the doubt that you said negative. So good job. Negative 119.7. And now we'll go to the differential form of the first law. It's steady state. Okay, so let me write out the whole thing. So we have that dE dt is equal to Q dot minus W dot. dE dt is 0 because it's steady state. So 0 is equal to negative 119.7 minus, okay, what do we know about the works? There's work being done on the shaft by the surroundings. So that's a negative input work of 60 kilowatts. So that's negative 60 times 10 to the third. And then our system is doing work on the surroundings through that W2. So this is plus W2 dot. And so 119.7 is equal to 60 times 10 to the third minus W2 dot. And so W2 dot is equal to pretty close to 60, but not quite. So 60 times 10 to the third minus 119.7 is 59.88 times 10 to the third watts. Okay? Any questions about that? Okay, that's all. Yes?